Alright, in the previous video, we built a convolutional neural network and trained it from scratch to classify cats and dogs. But training a complete CNN from scratch is not always the best solution, especially when we have a limited amount of training data. In this video, we're going to learn about transfer learning. The main idea is simple. Instead of starting from zero and training every layer ourselves, we can use a model that has already learned useful visual features from a very large dataset. Then we can transfer that knowledge to our new task. For this example, we will use VGG16, which was previously trained on the ImageNet dataset. VGG16 has already learned many useful visual patterns, such as edges, textures, shapes, and more complex objects. So instead of asking our model to learn all these features again, we can reuse the knowledge that VGG16 already has. This is the main idea behind transfer learning. Alright, my name is Armin Hassanzadeh. Before we get started, make sure to subscribe to my channel and hit the bell icon so you don't miss any future videos. First, we import the libraries that we need. We import OS because we will work with directories and dataset paths. We import matplotlib pyplot so we can visualize our training results later. And we import keras from TensorFlow because we will use to lead the pre-trained VGG16 model and build our new classifier. Now we load the VGG16 model. We use weight equal to ImageNet, which means we load the weights that VGG16 learned while training on the ImageNet dataset. So we are not starting with random weights. The model already contains knowledge learned from millions of images. The next important parameter is include top, that it's equal to false. The word top refers to the final classification part of VGG16. A complete VGG model has two main parts. The first part is the convolutional base, which learns and extracts visual features. The second part is the fully connected classification part, which uses those features to predict the final class. By setting include top equal to false, we remove the original classification layers and keep only the convolutional part. So we're using VGG16 as a feature extractor. Finally, we define input shape equal to 150 by 150 by 3, meaning our input images have a height of 150 pixel, weight of 150 pixels, and 30 color channels, red, green, and blue. Now let's look at the architecture of the VGG16 convolutional base. As we can use VGG16, that it has contains several convolutional blocks. Inside these blocks, convolutional layers learn visual patterns, while pooling layers gradually reduce the spatial size of the feature maps. Our input image starts with a size of 150 by 150 by 3. As the image passes through the network, the height and weight become smaller. After the final convolutional block, the output has the shape 4 by 4 by 512. That 4 by 4 represents the remaining spatial dimensions, and the number 512 means that the final convolutional block produces 512 feature maps. So whenever we give an image with the shape 150 by 150 by 3 to this model, VGG16 converts it into a feature representation with the shape 4 by 4 by 512. You can think of this output as a compact representation of the important visual information in the image. The convolutional layers learn how to extract useful features. Later, we will use a new classifier to decide whether those extracted features belong to a cat or dog. All right, now we need to prepare our dataset. If you're running this on your local PC, you can simply define your base directory and the path for training, validation, and test it like this. However, if you're using a Google Colab like me, we need to set up the Kaggle API first. So I downloaded before, and you can find it in my previous video how we can bring it from the Kaggle website. And we create the Kaggle directory, move our Kaggle.json file there, and download the dog vs cats dataset, unzip everything, and so on. So this process, as I told you, you can find in my previous video. Now we define where our original dataset is located, and then we create our subset directory structure with separate folders for training, validation, and test splits. Inside each split, we create separate folders for cats and dogs. So we have cats and dogs folders inside training, validation, and test directions. Um, This way, our data is organized and ready for the next steps. So I quickly go forward these steps because we did before. Now we copy our images. We take the first 1,000 cat images and 1,000 dog images for training. Then the next 500 cat images and 500 dog images go to validation. And finally, the next 500 cat images and 500 dog images go to testing. This gives us a balanced dataset with 2,000 training samples, 1,000 validation, and 1,000 test samples. Now, here's the key part. We create an image data generator with rescale to 1 over 255 to normalize our pixel values. Then we define an extracted features function that takes a directory and the number of samples we want. We create a features array with the shape sample count 4 by 4 by 512 and a labels array with the shape sample count. We initialize a generator using a flow from a directory with our target size of 150 by 150 and batch sizes of 20 and binary class mode. Then we loop through the generator for each batch. We use our VGG16 convolutional base to predict the features, store them in our features array, store the labels, and increment our counter. We keep going until we've processed all the samples. Then we break and return both the features and labels. So this function essentially runs all our images through VGG16 and gives us the extracted features ready to go. Now we run this function 3 times. Once for our training set with 2,000 samples, once for validation with 1,000 samples, and once for testing with 1,000 samples. And just like that, we have all our extracted features and labels ready to use. So next, we reshape our features. Instead of keeping them in the 4 by 4 by 512 format, we flatten them into a single dimension of 80,192 features. We do this for all three sets: training, validation, and testing. This reshaping makes it easy to fit these features into our new classifier. All right, now we built our classifier network. We create a sequential model with an input dimension of 8,192 features. This goes into a dense layer with 256 unit and relo activation. Then we add a dropout layer with a rate of zero point 0.5 to prevent overfitting. Finally, we add our output layer with 1 unit and Simon activation for binary classification, cats or dogs, sorry. So we've used the pre-trained VGG16 model for feature extraction, and now we only train these newly added layers. We compile our model with the RMS prop optimizer and a learning rate of 2 E minus 5 use binary cross entropy as our loss function and track accuracy as our metric. Then we fit our model for 30 epochs with a batch size of 20 using our training features and labels and validating on our validation set. As we can see from the results, the accuracy increases significantly. uh, 89%, around 90%. This is the primary idea behind the transfer learning. We're leveraging a powerful pre-trained model to achieve great results with much less training data and time. So, as we can see also in the plot, our results. As you can see, our model has overfit also, and in the next videos, we will talk about it and how we can solve it. So, thanks for watching, and see you next time.